Grazie per essere intervenuti. È un piacere avere qui oggi Luca Pagano, dell'Università di Ferrara, che ci parlerà dell'Observing the First Light of the Universe con lo Stars and Future of Perspective, veramente sul Microwave Cosmic Background, del quale lui è un esperto per aver girato vari. Ora è all'Università di Ferrara, ma nella sua biografia c'è sono degli importanti pericoli al Jet Propulsion Laboratory della NASA in California. Mi sentono? Non lo sentirete perché parla in inglese, ma si è laureato a Roma alla Sapienza e questo qui
leggerissimo accento
romano e ha avuto una successiva esperienza ad Orsay e ora appunto è sta all'Università di Ferrara. Grazie e prego.
Okay, so first of all, thanks to Peppe for the kind invitation. It's the first time for me here in Catania, the department. So it's a real pleasure to be here. So the idea, I mean, I had some discussion with Peppe about the talk, and what I will try to do today is to give you really a broad overview of the status of the CMB observations, starting from an historical perspective at the beginning, and then I will try to guide you through either the data analysis perspective and also theoretical predictions. I will then tell you what is the status right now, and then I will try to give you a perspective about what is the future of this field. And also at the end, if I have time, I will try to also highlight some potential issues that we have to overcome for reaching the scientific targets. So I will start since let's say the beginning of what we now call modern cosmology. We can really mark the beginning of this science with the discovery, with the observations of Edwin Hubble, that almost 100 years ago, observing galaxies using the telescope of Mount Wilson in California, by the way, very close to Caltech, to JPL. There was during the firestorm in California, it reached almost the telescope. Also, JPL was closed for the same reason, but also the observatory was at risk. And the measuring spectra of galaxies from this telescope, he realized one thing, that the further the galaxy are, they seem to move faster away from us. So all the lights of the far galaxies is redshifted more than the light of the closest galaxies. And so he immediately put these two informations together and came out with a simple solution to this thing, that the universe is not static, but is expanding. Okay, so today is a given size, tomorrow is larger, and in the past it was smaller. Okay, so this really marks the origin of the born of modern cosmology, because people taking this information started to formulate theories about the evolution of the universe. So departing from the idea, the very common idea at the time, the universe was static, people started playing with, they had already a theoretical framework for handling the expansion of the universe, that was general relativity. And already, I must say, few years before the measurements of Hubble, people already started playing with metrics, and they were coming out with equations and metrics that were able to describe an expanding universe. Okay. So This is mainly due by Lemaitre in particular, but or Robertson, Walker a bit later, Friedman at the same time. So already in the mid of the 20s, just 10 years after the formulation of general relativity, people already had in their hands equations able to describe expanding universe. So when the discovery of Hubble came out, they have already theory ready for being used. So other people at that point jumped in, and in particular Halpern, Hermann in a seminal paper in 1948, and in the same year, 1948, Gamow also came out with another paper, all of them published on Nature, where they basically put this information together, and what they realize is a simple thing, that if today the universe has a given size, yesterday was smaller, and being smaller, if you think that as a gas, it was denser and in principle hotter, okay? And so if you go back in time, you can reach one point in which all the energy, all the matter and the radiation was concentrated in one singularity. They came out with the idea of what we now know, theory of Big Bang. Actually, they were calling this singularity primordial fireball. Actually, Big Bang came out by Fred Hoyle mocking. They started mocking them, calling this crazy theory the Big Bang theory. Okay, of course. They realized this thing of this possibility of the Big Bang, and also they came out with a possible way of verifying this theory. That is the fact that if in the past, if you think that universe started from a singularity and then started expanding, when the universe was very hot, the scattering between particles were very efficient, and all the particles in the expansion of the universe start to decouple from the primordial plasma, one after the other, based on their mass and or the efficiency of the interaction with photons. And at some point, when only photons and electrons were coupled together, at some point the universe is so large and so the density is so low that the scattering Thomson between electrons and photons becomes inefficient. And at that point, photons are free to travel toward us, okay? You have the recombination, what we call recombination. You form neutral hydrogen, and photons from that point on have the freedom of travel without having a probability of interacting with matter, which is very, very, very low, okay? So the universe becomes transparent. And I find always, I mean, this is a picture I took from, by the way, APJ made a fantastic job in the last years, rescanning all the papers, the whole papers. And so there are old figures that are have a super high quality. This is one of them, and this is a plot of this paper of Dickey, Peebles, Roll, and Wilkinson in 1965. But you can find images like this even before that. And you have on the x-axis, sorry, the pointer is a bit faint, but you can see it. On the x-axis, you have radius of the universe in some arbitrary units, where now is 1 is basically describing here in the metric the scale factor. And you see clearly that at that time they already realized that at some point here, this dashed line, you have plasma recombines. This marks the moments of the universe where the radiation decouples from electrons, and you have the formation of the cosmic microwave background. So at that point, at this point, we have a clear prediction, and people started looking for it. And in the 1965, two people, these two guys here, Arno Penzias and Bob Wilson, they were working in the Bell laboratories. They had this big antenna. They were measuring at low frequency. I mean, between millimetric and radio. It's written here. Yeah, 4 gigahertz. You see there, here. And they had a noise that they could not explain. Okay, they had a noise in their measurement, and they could not get rid of this noise. Okay, so they started arguing what is the nature. Of course, they check for atmospheric emission. They check for all the possible potential systematic. And luckily, I mean, I think Bob Wilson was in contact with Roll, that was working at Princeton at that time, and Roll was in contact with Peebles and Wilkinson that were working to the cosmic microwave background. Basically, all these people joined the effort at that time, and they realized that the radiation they were measuring and this noise they were measuring potentially could be the relic radiation of the Big Bang. They made all the possible tests, and at the end they wrote a seminal paper on APJ in which they wrote this excess temperature is within the limits of our observations, isotropic, unpolarized, and free from seasonal variation. They measure for almost 1 year, and then we compute the remaining unaccounted for temperature to be 3.5 plus or minus 1 Kelvin at 4 gigahertz. Okay, this is the first detection, the first, I must say, recognized detection of the cosmic microwave background. Why? Because people at that point, knowing the target, started looking at all data, basically, and they realized that there were papers there in which you clearly see the line, okay, you clearly see the radiation measured in other 10 years before. People already saw the cosmic microwave radiation, but they could not recognize. It's full of books and articles saying there is this excess here with an antenna temperature of blah, 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 detected at this significance of no particular importance. That was the level of not even realizing that could be, because of course there are two different communities. There is a community of theoreticians, mainly in Princeton, that were working actively on that, and other people, especially astronomers, and they were not really communicating because they were in different communities and there was at the different times, of course. So this is the first detection. Of course, since theoreticians were predicting that you should see a black body, and of course, if you have a black body radiation of roughly 3 Kelvin, the peak of the radiation, it's a much higher frequencies, of course, if you take a black body. So they were looking at the tail of the distribution, okay? So if you want to really measure and then check that the radiation is a black body, you have to measure at high frequency. What is the problem? The problem is that atmosphere is transparent in the radio region, but is not transparent in the millimetric. And so they started thinking, okay, we should use balloons. And for example, here in Sicily, then in Trapani, for more than 1 decade, I think late 70s and the 80s, there were people in Trapani sending balloons trying to measure the cosmic microwave background radiation. And they were sending balloons from Trapani and then collecting the payload in Spain and redoing. Francesco Melchiorri did that for more than 10 years, but other people were coming here for measuring the cosmic microwave background radiation. The other, of course, possibility was to fly, to put instruments on rockets. But of course, the best solution is to build a satellite. You go above the atmosphere and you can observe from the space. So John Mather and George Smoot, Berkeley and Goddard, they joined the effort and they built this satellite that I'm picturing here, COBE, and they launched it in 1989. And COBE had on board, of course, an FTS, so a Fourier transform spectrometer, and they could measure finally the whole spectrum of this radiation. And you see, this is I think you saw this image in other situations. This is an amazing plot and a perfect confirmation that what we really see is an almost perfect black body with a very small deviations. These fundamentally serve as a definitive confirmation that the Big Bang model is actually correct. What is the interpretation of this radiation? This interpretation is what I said before. This is the radiation emitted at some point after the Big Bang, roughly 300,000 years after the Big Bang. It represents what? It represents the relic radiation of the last scattering, the last Thomson scattering that electrons had with photons. It's very isotropic. They realized pretty soon tiny fluctuations on top of that. Here I put, you see here, DMR instrument. This is a kind of a less known instrument, but there was another instrument, actually, there were other two on the COBE experiment together with FIRAS. One of these was DMR, and DMR was an instrument they put on board with radiometers for measuring the anisotropies of this radiation. They measure, of course, the monopole. You see here this orange plot. They measure, of course, our motion with respect the black body, the CMB surface, so our peculiar velocity, so the dipole term, and then below that, at a level of roughly 10 to the minus 5, the monopole, these anisotropies you see here. Here you see it overlapped with this galactic emission, but if you go at high latitude, galactic latitude, you see this granularity. Those are the anisotropies of this radiation. So at that point, you have confirmation of the black body, the cosmological origin of this radiation, the perfect black body, which make it even stronger, the cosmological origin of this radiation. And they found these small anisotropies on top of that. So people could form a credible theory for the thermal history of the universe. After the Big Bang, we have a kind of a primordial soup where protons, electrons, neutrons, other particles are all coupled together. The temperature is too high and the scattering is so efficient that it's a coupled plasma altogether. During the expansion, so of course the universe cools down. A few minutes after the Big Bang, when the temperature is low enough for forming the light nuclei are formed, and so we have what we call the Big Bang nucleosynthesis. That was, by the way, another prediction of George Gamow that was confirmed by observations that happened later. So we have formation of helium, deuterium, and lithium. And then a while later, there is a typo here, 300,000 years, 380,000 years after the Big Bang, the universe is cool enough to form a neutral hydrogen. That from that point on, the universe becomes transparent to photons. And these photons are what we now call the CMB, the cosmic microwave background. The density perturbation of the plasma, okay, of course, that were present at the last scattering get imprinted in the radiation that gets emitted at that time, okay? Of course, this means that if you study the characteristic of this radiation, you have information of what? You have information of all the evolution of the universe before the recombination, okay? It's a way of measuring what happened before the recombination. Of course, this is not only true because then you have interaction with matter due to the gravitational lensing, and so you can also use the CMB as a backlight. But I will tell you about that later. Okay, at this point there are still some problems. First of all, why regions that are not here, you see from here, why regions that are not causally connected? So if I look in two different directions, I see the same radiation, okay, the same temperature. How is possible that regions that were not causally connected at the recombination show the same temperature? And this is one problem. And the other problem is gravity can amplify the fluctuation, but cannot create them. So you need, at that scale, you need a mechanism that produces this fluctuation. You need seeds for the fluctuations. What is the solution of that? The solution of that is quite famous, is inflation. I mean, it's a cosmic inflation, of the inflation, economic inflation. So it's the cosmic inflation. And actually, the cosmic inflation was, at the beginning, proposed for solving a different problem. The origin of, especially in the first paper of Alan Guth in 79, the idea was to give a reason to the very simple problem. It was the fact that we could not observe magnetic monopoles. There was Dirac started working a lot on the quantization of the electric charge, and he was working a lot on the magnetic monopoles. And there was this strange thing that you could not observe magnetic monopoles. And so people started looking for mechanisms that could get reason of this lack of observation. But when all this picture of the Big Bang came out, the idea of inflation was actually pretty reasonable for explaining and for solving the problems I was mentioning before. What is this inflation? It's a period of an accelerated expansion of the universe driven by a scalar field, okay, in the early phases of the evolution of the universe. Inflation explains perfectly homogeneity and isotropy of the observable universe, and also have peculiar, two important predictions. One is the fact that the universe needs to be flat, okay, and so removes any fine-tuning problem to the flatness of the universe, and also helps in if you want, gives the reason for the seeds that create the primordial perturbation that then we see imprinted in the CMB radiation. In particular, from the inflation, you can get reason to the spectrum for the scalar perturbation and also tensor perturbation. You can produce through inflation both scalar and tensor perturbations. What is the origin of this? Basically, the vacuum fluctuations after the Big Bang, thanks to the inflation, get amplified by these accelerated expansions and become the perturbation that then we see on the CMB field. At this point, we have a kind of a theoretical framework that we can use, and we can start observing things. And so people at that point focus their attention on measuring the power spectrum of the temperature of this radiation. Here I put this plot because I just to let you, to let you know that of course COBE had a very rough and very wide beam, so very low resolution observations. But information in the CMB are also present at small scale. So if you increase the resolution of your instrument, you gain more and more information because you observe more scales and you can obtain increase your knowledge about the universe. Okay, so as I said, COBE opened the era of the power spectrum of observations, and since the original seeds are random fluctuations, theories cannot predict the phases of these fluctuations. You cannot predict if you have a bright spot in one direction and a cold spot in another direction. You can only predict statistical properties of the field. And since the fluctuations, the theory predicted fluctuations were nearly Gaussian, okay, so you are basically observing at zero mean Gaussian fluctuations in the sky, what you can do, you can take this field on the sphere, expand it in spherical harmonics, and then use the spherical harmonics for compute the power spectrum. So from measuring the power spectrum of the CMB, you can obtain all the information you need, you can extract from that field. Of course, there is a fundamental problem that is related to the fact that we only observe one universe, okay? So we cannot take an average over realizations, but what we can do is came out with an estimator for the power spectrum that basically uses the quantum number m and averages over the quantum number m for obtaining an estimated power spectrum that needs to be compared with some theoretical predictions. Okay. Okay, so here I will jump a bit ahead, and then I will go back on these plots. But I want to show you how the power spectrum CMB looks like. This is the temperature. This is a beautiful image published by the Planck collaboration in more than 10 years ago. And you see here the power spectrum of the CMB with some measurements. But I want you to focus here on one thing. That is the fact that you have this green shaded region here, okay, and then becomes narrower and narrower, okay, across the various scales. And this is what we call cosmic variance or an intrinsic variance. This is due to what? To the fact that having just one universe on which we can measure, and we use basically the ergoting theorem for extracting the power spectrum, we have that at a given L, we have a finite number of m on which we can average 2L plus 1, okay? So this gives an intrinsic variance associated to the power spectrum that is particularly visible at large scales. So we know that the largest scales are dominated by the variance of the intrinsic variance of the field, due to the fact that our estimation comes from a single realization. Okay. Okay, so but if you have this, you want to compare it with theoretical predictions. So we need to compute theoretical predictions. How can we do that? So I will not enter into many details here, but of course what you need are the initial conditions. So you need to parameterize in some way the power spectrum of the inflationary perturbations. And since many of the more natural inflationary models predict nearly power laws or power laws shapes for the perturbations, the reasonable thing is to parameterize that in this way. So with an amplitude and then a spectral index. Okay, here K star is kind of a pivot, is where you basically measure the amplitude, at which scale you measure the amplitude of the perturbations. Okay, this is for the scalar perturbation, this is for the tensor perturbation. In some occasions, instead of fitting for the two amplitudes, okay, of scalar and tensor perturbation, you can fit for the scalar and then fit for the ratio between the scalar and tensor perturbation. This is the parameter, it's quite famous, it's called R, which is the ratio between tensor and scalar perturbation. But of course, this is not enough, because you need to include in it also the physics of that is the physics of the plasma. So you need to parameterize also the energy content. We don't know a priori the energy content in the universe, and so you have also to include in the prediction, the calculation of the prediction, the content of matter, of potentially dark energy or density of cosmological constants, baryon matter, neutrinos, and so on, extra radiation. And then the other free parameter is the expansion rate, H naught, which is the Hubble parameter. This is from the, let's say, initial condition and parameters on the model. But then on the other side, you have, of course, the physics. You have to include the physics in the computation. And this is also, it's quite reasonable. You need, on one side, what happens at the recombination, which is Thomson scattering. So you need the physics of Thomson scattering. Then you need the physics of the quantity of ionized fraction function of time in a plasma in equilibrium. And again, this is an old calculation made by Sa more than 100 years ago and was perfectly fine, actually with some modifications were perfectly fine for describing it. Then you need perturbations, and so you need linearized general relativity with perturbation on top of that. And then since you are describing the evolution of a plasma, you need Boltzmann equation for the angular distribution function, how this evolves with the scattering. If you put everything together, you can write the theoretical power spectrum as a kind of a convolution, if you want. It's an integral over the initial perturbation, so the P of k, the one that are the inflationary perturbation, times what? Times a transfer function. So it's something that translates the initial perturbation into the perturbation of the plasma at the time of the recombination. And then, of course, you have also a projection term, which is a spherical Bessel function. So if you do that, you can come out with a, I mean, this is a cartoon plot for giving you the idea of where you can look at for measuring, for determining the parameters of the model. You have, of course, at large scale, a super horizon perturbation. Then the position of this first peak give you the geometry of the universe. So measuring it, you can measure the geometry of the universe. The height of the first peak and also the other peaks give you the content in terms of dark matter. And then the secondary peak give you the relative height of the secondary peak, give you the quantity of baryons. And then the tail is related to diffusion, to extra radiation that can be present at the time of recombination. Of course, you can do that in a more proper way. You can vary cosmological parameters, observe how the power spectrum is. I'm going a bit slow. I will try to speed up a bit. I have 45 minutes, right? Or I can go up to 1 hour.
You can go to 2 hours.
Really? No, I want to see. There is a, let's say, Geneva Convention that tells you that you cannot overcome. Okay. So and so here you vary cosmological parameters, and you see how varying cosmological parameters the power spectrum change shape. We'll go a bit faster on this, then we can go back on that in case. Okay, but is it everything is contained in the temperature power spectrum? No, you can get more information if you observe also polarization. Why that? Because first of all, Thomson scattering, if there is a quadrupolar anisotropy at the time of the scattering, okay, produces also linearly polarized radiation. Okay, so you can extract information measuring also polarization of these polarized radiation of the CMB. Okay, and again, how you can do that? Same game. You go to harmonic space. In this case, instead of using scalar spherical harmonics, you use a spin 2 spherical harmonics for the nature of the field that you are observing. You expand that. You can expand that in. You see this combination here. You expand in spin 2 spherical harmonics. Then you can recombine in two scalar quantities that have peculiar properties. They're called E and B modes in analogy with the electromagnetic field. So one has this typical curve-free pattern like electric field, and this one and the B modes are these vorticus patterns typical of the let's say divergence-free, so magnetic field-like. The interesting thing that doing this, you can from calculations realize one thing, that scalar perturbations create only E modes, but not B modes, at first order at least. And tensor, so gravitational waves perturbation, create both E modes and B modes, okay? And this means that basically if you observe B modes, is a direct measurement of the tensor perturbation, of the inflationary tensor perturbation, okay? So again, this is as before I show you the Planck power spectrum. Here is the Planck power for temperature. Those are Planck power spectra for polarization, TE and EE. Oh, I'm sorry, I missed that, and this is important. In principle, given the scalar and pseudoscalar nature of the two combinations you built in the E modes and B modes, it's pretty easy to check that B modes do not correlate with the temperature and the electric-like pattern. So only the BB power spectrum can be generated by B modes. There are no correlation with the other fields. This is important for later. Okay. Again, dependency on cosmological parameters. You change parameter and you see how the power spectrum changes with the parameters. And then let me go to the last observable that I would like to highlight, which is the lensing. I mentioned that before briefly, and the idea is it's pretty simple. So far we said, okay, I want to observe the radiation coming from the scattering, okay? And this tells me what? Tells me about the status of the plasma 300,000 years after the Big Bang, okay, and fluctuations on that surface. But you can think in a different way. Imagine that what you observe, what you have, the radiation can serve as backlight, okay? So you have that photons emitted at the last scattering traveling towards us, okay, gets deflected by the structures of the universe. This is what is that's a typical generativity effect. So this is gravitational lensing. Also, CMB radiation undergoes to the same kind of deflection. So people started thinking. So here you can write the equation for the deflection. This is a really very easy calculation. You do that for sure you'll do that in your courses. And then you have a part that is related to the geometry of the lens, and the other part is related to the matter potential. So the distribution of matter in the universe affects how the CMB radiation gets propagated during the expansion of the universe. Okay? So this is a cartoon plot that shows you what happens. You have unlensed, so fields, temperature, E modes, polarization. This is the gravitational potential. And then when you apply, this is over-exaggerated, you start having this kind of deflection or modification or distortion, actually, of the field, very exaggerated for temperature, E modes. And the funny thing that despite in principle scalar perturbation do not produce B modes, when you have the effect of the lensing, scalar perturbation, so E modes, can be transferred, can be deflected in such a way that you have also B modes polarization. What are the effects on the effects on the power spectrum? First of all, the effect of lensing is basically on the CMB power spectrum. This is for temperature, but you can see the same also for E modes and the correlation between T and E. One of the effects is to smooth the peaks. Okay, the more matter you have, the more lensing effect you have, the more you basically shuffle basically the scales, and you tend to average away the fluctuation. This is over exaggerated, okay? If you want, this goes from AL0, means no lensing, up to AL10, which is 10 times what GR predicts. AL equal 1 is exactly GR. So this is over exaggerated, but still this is observable. The other thing is what I told you before. Lensing potential is able to remap E modes into B modes. Okay, so even if the primordial sky had only E modes, thanks to the lensing, you observe both a mix of E modes and B modes. You can compute that. This is you see here again, it's a kind of a convolution of the gravitational potential and a kernel, and then the E modes power spectrum. You see gravitational potential psi, the kernel psi, phi, and EL are the ALMs, the coefficients of the E modes. So you see, you generate these. I cannot see it anyway. The green line there. Okay, you see that. Then can we go beyond that? So we saw the effect on the power spectra. Can we go beyond that? Yes, we can, because sure.
Okay, now you show the effect of
Fantastic. This is exactly what I was. No, that's an excellent question. Of course you can. Yeah. And you can do that by I mean, imagine that you have a Gaussian field. Okay, you do the power spectrum. Okay, so you expand that in spherical harmonics. You get the spherical harmonics. The basis is complete because it's in the tie sky. That object by construction, this is just a Gaussian fluctuation, is uncorrelated. Each shell is independent on the other, full sky. Okay. If you have lensing uses a degree of non-Gaussianity that is visible in the correlation between the various multiples. So you can exploit the correlation between the multiples. Okay, you can see it from here. Okay, this is the correlation between two fields. It can be either the same field, TT, X and Y, like here. Okay, you write this. This is a kernel basically, and if you measuring the level of correlation that you have in your field, that level of correlation can be interpreted as the effect of the lensing, and you can invert it basically. So you can come out with a quadratic estimator that gives you back the psi L. This L, small l and capital L, you should interpret that LM. Sorry, it's a generic index for L and M together. Okay, so the psi L that you have here is exactly what you said, is the power spectrum or the ALM of the gravitational potential. Once you have that, you can go back in real space using the spherical the transformation, the spherical harmonics. Okay, the star spherical harmonics, and you can go from ALM to the real space and get the map. This is what? This is the map of the gravitational potential of the universe. It's a tracer of the dark matter in the universe. Exactly. So of course this is what you measure from the lensing basically. Yeah. This is the integral along the line of sight of all the matter encountered by the photons of the CMB. You have a kernel. You have a kernel in zeta if you want, or in tau if you want. So you have an. No. Okay. By the way, yeah, that's a fair question. It's an integrated effect. So that we can discuss later anyway. Of course, since we have ALMs, we can also do power spectrum. So instead of going in real space, you go in the power spectrum of the field. And this is the very nice power spectrum plot that was done by the Planck collaboration in the final analysis. So of course, as we did for the other spectra, also in this case, you can vary cosmological parameters, and this is how, for example, dark matter and expansion rate, when they vary, affect the lensing power spectrum. Okay, so let's go back to some history. We stop our the discussion about the history of CMB to at the time of Kobe, and then, as I said before, Kobe opened a new era, and then the rush of the search for anisotropies and the study of anisotropy started. This is the situation in 1998, where you see people. There were many observations. All of these were either suborbital, also either balloons or ground measurement. And the history of CMB was a long sequence of CMB observations, a long sequence of ground and suborbital experiments, alternated by full-scale measurements made, or full-scale, I mean also full-sky measurement coming from space mission. This is 1998. 3 years later, this is I put this plot because it's a friend of mine that did it more than 20 years ago, and also it is important because this is the status pre-WMAP, which is the second satellite we had in CMB, and I will discuss briefly about that in the next slide. But this is also important because this is the plot, or anyway, the data here, especially boomerang and maxima, that were able to confirm one prediction of the inflation that was, you remember, I said before, the flatness. And there is this famous paper by Paolo De Bernardis, a Nature paper by Paolo De Bernardis in more than 20 years ago, that presented the results of the boomerang balloon, and in which the flatness, effective flatness of the universe was of the geometry of the universe was confirmed. After that, oh, sorry, this is also important. In 2002, I mean, polarization was still missing at the time, but this experiment, DAISY, in 2002, made the first detection of polarization. Those are the cyan bars here. It was the first detection of polarization signal. After that, as I told you before, came the second satellite of CMB, that was WMAP. It was launched in 2001, I think. And then in 2004, the first year results came out. And this is, you see the black points here. Of course, it was much better. All the previous observations were made at that time. Then, of course, WMAP went for many years of observations, 9 years of observations, and here the final WMAP results in 2013. Of course, people studying the CMB from the ground didn't give up and said, okay, we cannot compete with WMAP on the large scales, but even because we cannot observe the entire sky from the ground, but we can complete the observations of satellites with on the small scales. And this is the status of the CMB observations in 2013, just before the first release, the first Planck, the first release of the Planck data. So you have WMAP dominating at small hells, and then these two experiments act on the Atacama Desert and SPT at South Pole, that were measuring very well the smaller scales. And then Planck. Planck is the third generation of CMB satellites. I work on that, so I put a couple of slides on it, because basically what we currently know, much of what we currently know on cosmology from CMB is due to what Planck did and what Planck measured in the, let's say, roughly 10 years from the launch to the final release. I mean, I will not spend time on the configuration, but those are the main results. This is a slide that shows the temperature and polarization maps on the left. And then the last one is the plot I was showing before, the one of lensing potential, which is, to me, is amazing. This plot here, and then all the power spectra. You see that the Planck could reach if compared to what WMAP did. You see, WMAP here goes up to 1,000. WMAP, Planck basically doubled the scales that were measured on the power spectrum. Of course, Planck finished their activity, and this is the status we have now. Temperature and B modes, fundamentally at large scales, are given by Planck observations, while small scales and B modes are given from ground experiments. ACRES PT, I mentioned them before, and then other two experiments are now, I mean, one is still taking data, Bicep Keck and Polar Bear. You were in Polar Bear, right, Pepe? So also was the first experiment, I guess, to observe B modes, right? The lens in B modes. Cool, exactly. So what we have learned so far, that's an important thing. So first of all, there is a clear evidence that we cannot justify the observation of CMB only using baryonic matter. A certain level, and actually more than a certain level, more than much more than the like roughly a factor 5. There is more dark matter than baryonic matter in the universe. So we need CMB only observations cannot be explained without including dark matter. Dark energy is also fundamental. We are not compatible with dark matter, only matter observations, okay? Only matter energy content in the universe. So dark matter and dark energy are necessary. And this is confirmed also by other observations coming independently, coming from supernovae, for example, and BAO. The geometry, as I said before, is flat, so the confirm of the flatness, which was a generic prediction of the inflation. The baryon density we measure, we can check it with independent measurement, and is coherent with the, I told you before, with the Big Bang nucleosynthesis prediction. So people measure primordial helium and deuterium and compare what comes inferring from that the abundance of baryonic matter, and this matches perfectly what CMB is telling us. The initial conditions of the inflationary perturbation, the scalar inflationary perturbation, are slightly red tilted as generic. There's a generic prediction of many of the most simple inflation models. There is no evidence so far on primordial non-Gaussianity, even if many of the inflationary models predict a certain level of non-Gaussianity. The structural formation scenario is coherent with other cosmological probes and with sum of neutrino masses, which is lower than 0.2 electron volt. The number of neutrino species is consistent with 3 species as a standard and as in the standard model. The Hubble rate, so if you want, this is a way of measuring potential extra radiation coming from species, for example, that decay pre-recombination and leave an extra radiation in the plasma, the recombination. Hubble rate inferred, this is an interesting thing, is in tension. It's way low. It's roughly 5 sigma low than what instead you infer from local measurements, so using Cepheids and supernovae. And then finally, remember we said before, primordial gravitational waves, so tensor perturbations coming from inflation. We could, we know that tensor perturbation are at the level of roughly less than 3%, less than the scalar ones. Okay. This is what we did so far. Okay, 54. Let's try to be a bit fast. Yeah. What is the frontier now? So first of all, since we know that B modes can only be generated, primordial B modes can only be generated. I mean, it's a unique prediction actually of inflationary models. One of the targets, the main target of future experiments, is to measure these primordial signals. So much of the focus is on the B modes, trying to detect B modes. And what you want to do is basically, what we want to do is try to measure this power spectrum here of B modes in two windows, one at very large scales, so only accessible from the space, and one at intermediate scale around L equal roughly at the degree, which is what we call recombination peak, that can be observed also from the ground. An important thing is that lensing B modes, the one I was mentioning before, so the B modes induced by lensing, in this case, are acting like a foreground. So they need to be removed and be characterized in order to exploit the full potentiality of the future experiments trying to measure in this region. This is one target, and the other one is more. I mean, it's more related to neutrino physics, and is related to what? Sorry, no, we'll stay here. Measure neutrino mass. Okay, this is another target, and the other one is improving our constraint on the effective number of relativistic species, because potentially we could, if we find an excess of radiation, of a lack of radiation, this could be an hint of extra species that decay at some point pre-recombination, okay, or like particles that are not present in the standard model, or we can have, for example, low rating temperature. Okay, so let me go fast. This is how these parameters affect the power spectra. And so last minute and a half, I will focus it on what is the current status of observations, or what we want to do in the near future. So I'm showing here two experiments. One is, I mean, it's not so publicity here because Giuseppe is one of main contributor of this experiment. Also, the other one I will mention later. So there are two major. I mean, there are more than two, but those are the two that are very promising. One is the Simons Observatory, which is a set of telescopes in the Atacama Desert that try to measure both all the scientific targets I was mentioning before. So they are active, and they're trying actively to constrain extra radiation and the sum of neutrino masses, and also trying to detect primordial B modes on the recombination peak. The interesting thing, this is a fantastic moment for joining the effort, because some telescopes started taking data last year in May, and the large aperture telescopes, more focused on the relic radiation, started operations last week, basically. So there will be, I think, this week press release about the first light. This is one, so this doesn't matter. Okay. The other effort is a bit more long-term effort, is satellite. This will be the fourth generation of CMB satellites, LiteBIRD, which is a JAXA-led international mission that was selected in 2019. And the idea of LiteBIRD, instead of focusing on different scientific targets, is more focused on the primordial B modes, because it's trying to do this. It's trying to measure primordial B modes in the two peaks I was mentioning before. So trying to confirm the B mode signal, measuring both the recombination peak and the reionization peak at the same time. I think I stop here. I have other slides, but I think it's too much. And then in case we can go back on that if you have questions on that part. I left all the part of issues. Everything is fantastic. There are no issues. Ma non vale.
Thank you, Luca, first of all. No, a comment on what you said on dark matter implied by CMB observation. You said that...
No, that's a bit too much, probably, yeah.
Yeah, I don't know, but I wanted to if you can just have a comment on what do you think... so do you think also Mond in this case, so would be this...
No, exactly. That's a good point. No. I'm not really an expert on that and of that, and I think yeah, probably there is a parameter place in the parameter space where modified gravity can explain CMB observations. What I think it's very difficult, and maybe there are new studies, but I'm not aware of them, that can do that, but I'm not sure if, because you don't need only to fit for CMB data, but the problem is that you need to be compatible and to fit also the other cosmological data that are not CMB related. And this is very difficult. So find a unique solution for CMB primary, lensing, BAO, supernovae all together with modified gravity. I doubt that right now this is possible. And so somehow this is, of course, you might find a solution that excludes some data or other data. Systematics might be still there in some observational data sets. So it might be more complicated than that. But I mean, if you stick with the, let's say, the paradigm of baryonic matter, dark matter, and potentially dark energy, if you want to fit CMB data, you need both dark matter and dark energy. And a universe with only baryonic matter and dark energy doesn't work. A universe with only baryonic matter and dark matter doesn't work, and so on. Then, of course, the nature of these fields, that's, I don't know, it's quite, there are experiments that are trying to do that, and direct experiments that are trying to do this. Let me do a comment here. You know that, I mean, there is a strong Italian contribution to that, also a UniFE contribution in the Euclid satellite, and Euclid satellite will give us, will tell us a lot about the nature of dark matter and dark energy in particular very soon. So we will, it's a period that, I mean, it's a fantastic period for cosmology. There are probably more data than the amount of data, the amount of time for analyzing them.
First of all, congratulations. First of all, congratulations for the presentation. Then I want to ask, with this new theory about the timescape, have you heard of that? The
No.
new timescape theory about dark energy.
No.
There's no dark energy, but there's different, the matter can distort the frequency of light.
Okay, and so you can get rid of dark
Yeah.
Okay. No, yeah, maybe I went through some papers, but I don't know what to say in the sense that yeah, I mean, I don't know if because I saw papers, and some papers come out time to time that can explain some observable, but again, find alternative theories that can fit everything. That's quite a challenge. Somehow, this is an important thing. Sorry, maybe I went through that a bit quickly. The fact that the Hubble constant inferred, so the expansion rate inferred from CMB, so late time observations, and the Hubble constant measured by local by supernovae and then Cepheids, so the distance ladder, okay. 5 sigma tension, I mean, I'm looking at the people doing theory in this kind of fields. I mean, this is something that is quite exciting because this points to a problem in the model. And of course, the fact that, and this is a generic problem of cosmology that we need to recognize, that the fact that we have a lot of, let's say, effective components or paradigm like inflation is not fantastic, no? Because yes, you say dark matter, so you think at the gravity effect, or the gravitational effect of dark matter, but then this must be a field somehow. And so this field has properties. We need to know how this behaves, if it decays at some point, how is the behavior of this field. And this is difficult, no? It's something, it's an open question of both from the observational point of view, but I guess also from the theoretical point of view.
Thank you.
You showed the fluctuation at smaller scale observed by ground-based instruments.
Yeah.
What do they tell us actually? The smallest, this fluctuation at the smallest scales.
They basically tell us. They are. That's the tail is very sensitive to neutrino mass. Okay. And the particular extra radiation. If you have extra radiation in the universe, basically this extra radiation increases the free stream of over the fluctuations, over the baryonic fluctuations, and basically kills the baryonic fluctuation. So measuring the small scales is a way basically for strongly constrain the amount of radiation, of extra radiation in the universe. So for example, the parameter N effective I was mentioning at some point is very sensitive. It's very affected, or the other way around. Changing N effective changes a lot the tail of the power spectrum, and that's why, if you, I didn't mention that, but you see here now large aperture telescope, 6 meters aperture, going up to between 7 arc minutes and 1 arc minute. So the ground-based telescopes, large aperture telescope, are very high resolution in such a way that you can measure small scales, and this is done exactly for this reason. It's done also because you have a lot of ancillary science you can do. For example, you can work on transients, you can work on sources, you can work on other things. But the cosmological reason for that is to want to measure and characterize very accurately the small scales, because you can measure neutrino mass and extra radiation in that part of the power spectrum. Yeah, relativistic species, exactly.
Thanks, Luca, for an amazing talk. I wanted to ask more on the neutrino section. I wanted to know, like, which contribution they can, like, the future experiment they can give.
Yeah,
like,
I mean,
in terms of constraints and so on.
This is the plot. Yeah, this is the plots. I kind of went very fast on that. So in principle, and this is again, there is a lot of I don't know how to call it. Maybe concern. Maybe is the right word. Anyway. Yeah, concern is probably the polite way of saying that. On what cosmology can tell us on the hierarchy, for example. So in principle, this should be a granted discovery on future experiments. Okay, so Simons Observatory, for example, should tell us, combining anisotropies and lensing, if we should be able to exclude in case inverted hierarchy in principle, and confirm normal or the other way around. This is within the capabilities of these experiments. What's the problem here? The problem is that, first of all, is an indirect measurement. So you're not directly measuring the masses, but you are seeing the effect that the mass give to the structure formation and to the damping tail of the CMB. So the small scale we were discussing before. So clearly it's indirect measurement. So somehow it's model dependent, okay? Of course, everything is model dependent. When you measure something, you are assuming a model, okay? In this case, the problem is that when you are saying, okay, I'm measuring neutrino mass, you are, let's say, fixing some properties for dark matter, some properties for dark energy, and so on. And parameters are correlated. So it depends which assumptions you do. But again, a lot of information will come also from Euclid that is happening at the same time. So again, combining potentially these observations and Euclid, we'll have a better picture of, for example, what is the nature of dark energy that has an impact to what we say for neutrino mass. But in principle, if you simply take the standard cosmological model, dark matter, dark energy has a cosmological constant, all the things I said before, in principle, in a minimal extension of neutrino mass, you should be able, with SO, to distinguish between normal and inverted hierarchy. This is within the possibility of these experiments. It's should be done in a very close and very short time.